Okay, hey students, and welcome to the next presentation for Year 12 Physics. In this one, we're going to be looking at electric motors. So in the previous presentation, we looked at the force that's exerted on a charge that's moving through a field, and by extension, that means that a conductor that has a current inside a field will also feel a force. And in this presentation, we're going to be focusing on that conductor and the force that conductor feels. And since the conductor is experiencing a force, if you can put that on something that can rotate, like a motor, then that's going to experience a torque, which is due to that force at a particular point away from the axis. So just to recap, the right-hand palm rule, remember your thumb is the flow of positive charge, your fingers represent the direction of the magnetic field, and if you do that with a nice straight hand, the direction that your palm faces is representative of the force that the conductor will experience. So what we're going to look at is the anatomy of a DC motor. We're going to be looking at a simple motor. As I'll show you later on, they are a little bit more complicated than this. But let's just say that we have two permanent magnets that are creating a magnetic field between them. So in this particular case, you have a field that's occurring between the north pole of a magnet and a south pole of another magnet. Now, if we have that field running between those two magnets and we put a coil between them, so you can see that I've got a coil here in the middle. Now, it just doesn't look like a coil, but you can imagine that if I was to sort of draw that a little bit better, you might find that the wire will wrap around, say, a few times. So it'll go around and around and around and around, and then eventually it'll come back and it will turn in. So you have the current going through this coil. Now, the current will go up one side of the coil. It's also known as an armature, and then it will come back on the other side. So on one side of the coil, you have the current going in one direction, and the other side of the coil, you have the current going in the other direction. So before we look at this any further, I want you to see if you can demonstrate that you know what's going on so far. And I want you to copy this diagram down and then label and draw in the magnetic field, and then label and draw in the current going through the coil. And once you know the magnetic field direction and the current direction for each side of the coil, then can you tell me what the force is for each part of that coil? Okay, so I think the easiest thing to draw right now would be the magnetic field. So we know the magnetic field goes from north to south. So I can draw a magnetic field like this. Now, when I'm drawing my magnetic field, I should probably try and draw a little bit neater than I have, and I'm going to label that B. So the magnetic field is going from left to right. Now, the current in the coil, which I'll do with purple, the current will flow from positive to negative, right? So if this is the positive end here, that means that the current is going to be traveling here and then up. It's going to be traveling up on the left side. It's going to be traveling to the right at the top, and then it's going to be traveling down on the right-hand side before it returns to the power source. Now remember, the armature typically has many wraps of the coil, so the wires will keep going around, but the current will go in the same direction on one side and the other side it will go in the opposite direction. Now that we know the direction of the current, there's a few things we can do straight away. So we can see straight away that the current flow on the top and the bottom is in line with the magnetic field. Now that means that there is not going to be any force that's exerted on the conductor at that particular point. So now let's look at the left-hand side. So the current is going away from us, and the magnetic field is going from left to right, which means that the force should be downwards on this side of the coil. And you figure that out with your right-hand rule. I'm sure you've done that. And then on the right-hand side, the current is going towards us. So my thumb is facing towards me, and the field is going from left to right, which means that the force will be acting upwards. Now, isn't that interesting that each side of this coil is being forced to go in a different direction, which means if we have this part here, as an axis of rotation, that would mean that this motor would therefore rotate anti-clockwise. It will start to move anti-clockwise. And that is the basic principle behind how these motors work. Now looking at this diagram, you see that the left-hand side has a downward force and the right-hand side has an upward force. Now this is where we need to sort of add in something special. So as that coil starts to rotate, you can see straight away that the left-hand side, which will eventually go to the right-hand side, should still be experiencing a downward force because the current is still going sort of into the page on this case. So that force will always be down. In other words, once it switches sides, that force is actually going to be acting against the rotation. And that is true. So what you need to do is you need to add in a special component that every time the coil rotates, the direction of the current reverses. And that brings us to the commutator. The commutator reverses the direction of the coil current for every half turn. And if you have a look at the top right-hand diagram, you can see that if you look at just if you look at the whole picture, you can see that on the right-hand side, the force is always upwards, and on the left-hand side, the force is always downwards. Now, if you focus on just one particular side of the coil as it rotates, you can see that that particular side of the coil, it needs to change the direction of the force to keep it rotating. So when the left-hand side of the coil moves to the right-hand side, it needs to reverse the current so that the force goes back up and it allows the motor to turn, to continue to turn. Now, the simplest form of a commutator would be the split ring commutator, and that's the one that you see in the animation there on the right, and that's also found in these two diagrams at the bottom. The diagram on the bottom left, which is this one here, this one actually gives probably the clearest overview of the simple split ring commutator. When that coil is perfectly vertical, there is not supposed to be any current running through that coil. And you can see that why if you were to rotate, visually, if you were to rotate that red coil, then you can see that it will no longer be in contact with the electrical power supply, and it will therefore need to rotate by itself under its own momentum to get to the other side before then making contact and allowing the current to flow in the opposite direction and continue the rotation of the motor. So I think this diagram here really explains it well. If you have that armature moving, you can see that the forces are either going to be up or they're going to be down. And what you want them to do is every time you get a half turn, you want those forces to change direction. And that allows the torque to operate, in this particular case, act clockwise at all times. Now, let's talk about torque a little bit. You can see that when the armature or when the coil is perfectly parallel to the field, then the force that's being applied on those coils is perpendicular to the axes, which means that's when you have, so if you remember that torque is equal to RF, where F needs to be perpendicular. If you have that force being perpendicular when you have a horizontal armature, then that's when you have the maximum torque. And as you get closer to the vertical orientation, you can see that you're, like we did with the door handle example, you're going to be having that force has a much lower impact on producing some torque. And that's where you have this graph here. You can see that the amount of torque is at a maximum when you are horizontal, and it's at a minimum when it's vertical. And the other great thing about this animation is it shows you that the commutator is reversing that current once it makes it vertical. Okay, so what I've got here is a demonstration of the simple DC motor. So you can see that I've got this armature here, or this coil that's made up of a number of turns, and it can rotate freely, and either side I've got a magnet. So that way I've got a magnetic field that's going to be traveling from one side to the other, and I've got a current on one side that's either going to be going up or down, and on this side it's going to be going in the opposite direction. So the basic principle behind how this works is that if this was the positive end of your power supply, you can see that it makes contact with this copper wire, and this copper wire brushes up against this copper plate, and that's why in motors this contact point we say that these are called brushes into this plate, and then that goes through the copper windings around the coil and then back through the negative end to the negative end of the terminal. Now, importantly, as the motor rotates, you will notice straight away that that plate is no longer making contact with the positive end of the power terminal. In fact, once it reaches one half of a turn, it's reversed and it's now on the black side of, or the black terminal, which means that the current is going to be reversed and that allows the force on this side of the motor to always be in one direction, and the force on this side of the armature to always be in another direction, and it allows the motor to rotate. So if I set this up, well, I'll try and get it started with a stopping start. Let's see if I can get it going. Now what I'm going to do is, I know that there's contact that's already been made between the negative end of the terminal and this copper plate here, and here is where I need to make the contact myself. So motors are never, well, homemade motors anyway, are never perfect, but if I push this copper wire against the plate, it should initiate the rotation. Notice that the contact between the wire that I'm holding with my finger is not always constantly on to the commutator. So this is why we employ the brushes that actually maintain contact with the commutator, so that the current is at least pretty much always going to be on in one direction or another, except for the top of that split ring. And that's pretty much it. So that's a demonstration of the DC motor. So far in this presentation, we've looked at the more simplistic model of a DC motor, and that's where you just have a coil that's operating around sort of one plane, and then that rotates about an axis with across two magnetic poles. But if you actually open up a DC motor, what you'll find is something quite different, but it still operates on the same principle. So if you have a look at this picture in the bottom left, you can see that you still have the two magnets, and you still have the commutator. And instead of actually just having a single plane with a conductor going in and a conductor going out, what you've got is actually three poles. And in the diagram here on the right, it actually sort of dissects that a bit for you. And you can see that the commutator still does the job of switching the polarity of those poles. So instead of being a north pole, it will be a south pole. And the great thing about this design is that you can see that there's no point where you need to rely on momentum to keep that motor going through. So at every point in this rotation, there is a force or there is a torque acting on the motor, and that's why this is a more realistic approach. It's a little bit more complicated from a teaching perspective, but yeah, I think it's a really good way. And the diagram on the right really does highlight that essentially what you've got are three electromagnets that just turn on and off at the appropriate times to attract and repel them away from the permanent magnet poles, which is really cool. So with the concepts down, let's look at the calculations that you would need to have. So I've taken away that simple diagram that we've been looking at, and let's start defining a few regions, right? So you've got this length, and that is the length of your conductor, and this is the length of both of each side. You'd expect them to be the same in sort of a rectangular coil, and that length is the length that will be used in this formula here, because the force on each side is going to be equal to ILB, which is a formula we've covered before. But now we also need to start looking at the fact that a motor has a number of coils. So in this diagram that we've got, you can see that it's just sort of going up and back, and then that's it. But in reality, a motor will have it'll have a number of windings around the coil. So what you'd expect to have is another value like N, and I'm using a capital N, but you'll sometimes see a lowercase n instead. So each side at this stage will experience a force of F equals NILB, right? So it's just going to be the number of turns multiplied by that ILB that we've covered a million times before. And then you can start factoring in the idea that you've got two sides of two sides of the armature. So each side is going to be experiencing a force. So you've got a force on this side and a force on this side, and if they are both going to be contributing a torque, then what you would expect to have is you need to have 2 times, so that torque is going to be equal to 2 times that force multiplied by that R value, which is this one over here. So that R value is the distance between the length, the conducting length, and the axis about rotation. So to illustrate that a little bit better, if this is my axis of rotation and I draw in my coil and I'm looking side on, Okay, so I have a force coming down and the force going up. Then that R value is just going to be this one here. So now we're just looking at your basic torque component. So then we can keep deriving that when I've already got it there. But that means that the torque of that motor is going to be 2 times R times ILB. And then don't forget, you need to include the number of turns. And that's where you end up with this number here. So the torque on a DC motor is going to be 2 times the number of turns multiplied by RF, or R times ILB. So for you to solve a problem to do with a motor, you'd need to be given a few different variables. Before we do a calculation, let's just have a think about 3 important questions here. I want you to have a really good read of them, and then what I'll do is I'll go through the answers in a moment. Okay, so the first question says, at what part of the rotation of a simple DC motor would maximum torque be achieved? So we can illustrate that by drawing our motor. So there's the axis of rotation, there's my armature, and let's just say that there's a force that's being exerted down on this side and up on this side. Now, at this point, I'm happy to say that that is when the torque is going to be maximized. So if I was to draw that for a split second later, where it's looking like this, you can see that the force, there is now an angle between the force that's being exerted on the arm and the arm itself, which means that we would need to use F sine theta, which means no matter what, that result for the F sine theta is going to be less than if it was perpendicular. So essentially, the maximum torque is when the force is perpendicular to the magnetic field, or when the armature is parallel to the magnetic field. So question 2 is, explain why the net torque on a simple DC motor will be 0 when the coil is oriented up-down relative to a left-right magnetic field. So in my diagram, I've got the coil oriented up-down relative to a left-right magnetic field. Now, one way to illustrate this is by drawing the force vectors in at each point, right? So on this side of the coil, I might have a force going straight up, or if the current's going the other direction, the force would be going straight down, but it doesn't matter. And if I've got this particular case here, you can see that the force is now basically at 0 degrees, or parallel with the arm itself. So if we know that torque is equal to RF sine theta, in this case your theta is going to be 0, which means that the torque will go to 0. And the last question leads on from this particular situation. So you can see that there is a force that's acting outwards, or essentially stretching that coil outwards, and it's not going to create any torque. And the third question is asking, what would happen to a DC motor if a split ring commutator wasn't used? And effectively, what you'd expect to see is that the coil will essentially orient itself, the armature will orient itself the way it is in this diagram, and the motor will essentially become stuck. The current will flow through the circuit really fast, and you'll probably burn out the motor. So one alternative to this would be to generate a current that is alternating anyway, so an AC current. But what you have to be very careful of is you need to make sure that that current alternates at the exact rate that the motor turns. And although that sounds super complicated, those types of motors do actually exist. And finally, let's get a question done. So this is your typical motor question that you might find in the textbook or an exam. You've got a motor, it's got a 50-turn coil, so that means that the N number is going to be 50, and it has dimensions of 0.1 meters by 0.6 meters, and it tells you that a current of 2 amps flows through the coil, and it also gives you the magnitude of the magnetic field, which is 0.12 Tesla. So have a read of these questions, and then I'll go through the answers in a second. So part A asks us, what is the magnitude and the direction of the force exerted on side AB? And so if we look at this side AB here, we can see that it has a length of 0.16 meters, and we know everything else to answer the question. So the magnitude would just be the force is equal to ILB, and don't forget to multiply that by the 50. So it's NILB, and if you do that, what you should get is 50 times 2 times 0.16 times 0.12, and I get an answer of 1.92 newtons. and I'm going to be using my right hand rule to find out the direction of it. The current is going to the right, the field is going upwards, which means that to me, from my perspective, it is coming out of the page. And part B says, what is the magnitude and the direction of the force exerted on side BC? And that one is this here. And immediately you should recognize that since the magnetic field is directed upwards and the current is directed downwards, they are both acting parallel to one another. So you would simply just say no force. And question C says, what is the total torque acting on the coil? So we can start from scratch if we like. We can say that the torque is going to be equal to 2 times, because it's got 2 sides, times the radius multiplied by the force. And we've already calculated the force, so it ends up being 2 times, now the radius is going to be the distance between here and here. So that is our R, and that's going to be equal to half of that 0.1, so 0.05. And that's in meters, which makes things a bit easier. And 0.05 times 1.92. We're using that answer there. And if we do that, we should get 0.192 Newton meters. And question D, in which direction will the coil begin to rotate? So I'm going to take on my answer that I've got over here, saying that since that top side is going to be forced out of the page, that would mean that the bottom side will be forced into the page. And this is a really strange looking diagram. Like I said, you will come across them, which means, and my way to describe that would be to almost say, you can say it's coming out of the page at the top, or it's actually sort of clockwise, I guess. In exams, you're going to be given a lot more clear direction, or likely think you'll be given much more clearer direction than that. And that's pretty much all you need to know about the DC motor. You have a current going through a conductor. Essentially, it's happening on 2 sides of a coil. That coil has a number of turns. That coil is also known as an armature. Put that in a magnetic field. It's going to feel a force on either side, which creates a torque, and then it starts to rotate. It gets a little bit more complicated later on down the track, but if you start with those basics and you understand that, and especially understanding how a split ring commutator works, then you'll be fine. All right, thanks.